Okay, we're recording. Alright, let's get started. So this is a presentation on cracking software. We're going to go through a little bit of background on what that entails, and we're going to do a challenge presented by Wiremask. Wiremask.eu, that's where you can get the reversing challenge. Alright, so let's get started with purpose. So the purpose, we want to understand how a program works, and that way we'll be able to manipulate it into doing what we want it to do. And how do we do that? A couple ways we can do that. One, by patching, so that's where we locate parts of the code that they perform some kind of a check. So for example, do you have a proper license? Do you have the right key? It's going to check, yes, this key is correct, or no, this key is not correct. And we would remove that part, or tell it that the license is always valid, or the key is always valid, something like that. And then this one, I couldn't really think of what the name should be, but it's like lockpicking, and that's basically what we're going to be doing with this Wiremask challenge. The reason I use the term lockpicking, it's because it's like picking a door lock. We're going to reverse engineer the software so that we understand how it works, what kind of key it accepts, and then we're just going to give input that we know it's going to accept because we reverse engineered it and we know it's going to accept this. And this is pretty much how key generators are written. Somebody takes the software, they analyze the portion of code that checks the key, and we just generate keys that it'll accept. Alright, any questions up to here? Okay. So then this Wiremask reverse engineering challenge, I don't know if you can see that right there, but it's a really simple program where it just asks you what's the password, and it tells you if you got the right or wrong password. So really simple stuff. And the goal of this is to be able to find a key that works and no patching, meaning we're not going to change the code in any way. We're just going to find out how this program takes our input and validates it. Okay, so what do we need to do? We're going to basically put something in, see what it spits out, and we're going to work backwards from there. So this is skipping a little bit ahead. Let's go straight to it. Alright, so here's the link where you can find the challenge, wiremask.eu/reverse challenge weak checksum. Download it, unzip it, and the password to unzip it is given here. And the other thing that we're going to need is IDA Pro, or whatever disassembler debugger you like. IDA Pro is just easier because it's graphical. Okay. So IDA Pro free, if you just look that up, then you should be able to find it. 4.9, any of these should work. So hexrays.com, freeware version, yeah, 5.0, so that's the one. So if you don't have it, go ahead and navigate there, download and install that. Alright, so once you get that, you'll have the binary on your desktop. You'll have IDA Pro, so to open it up in IDA Pro, just drag and drop. It'll give you some information here. Okay, you can close the help. And it'll ask you what format. You can just choose the default stuff. Alright, the screen resolution here is pretty small, so what I'm going to do is put this into run mode. I'm just going to go ahead and run this so that we can get a little bit more screen real estate. So what I'm going to do is put a breakpoint on the starting point. Just go to the first instruction, which is a push EBP. Right click it, add a breakpoint, and we'll go to debugger up at the top and start the process. It'll ask you, make sure you know what you're doing, just hit yes. Alright, so in the back we have the window for the application. This is the checksum challenge that's running. And these are your IDA Pro windows. So right here, this is where our execution is. This is basically the code that's being executed. Right here we have our memory stack and our registers. So one of the prerequisites for this is to know a little bit about assembly. If you don't know what assembly is, it's basically mnemonic representation of machine code. Exactly what your processor is executing. So when you write a program in C, the compiler basically translates this into machine code, and this is exactly what the processor sees while it's running. So if you're not too familiar with assembly, just try to bear with me, and it should be fairly straightforward if you've done some C or Java programming before. Okay, so we started with our execution here. First instruction is a push EBP and move ESP into EBP. So again, if you're not familiar, the way that this Intel syntax for assembly works, it's taking whatever's on the right and it's moving it into the left. So it's destination, comma, source. Alright, and how about I just go ahead and run it, just so that we can see what this looks like. We run, it asks you for the password, you type in some password, and here it says we have an exception. So what I'm going to do is just run this natively without a debugger, just so that we can see what it looks like. I'm going to run this in command.exe. So we run it, it asks for a password, type in something like password, and it tells us we have the wrong password. So our goal is going to be to find out how this program takes input and validates it. We're going to find out what we need to do to get a key that's going to fit. Alright, so if you're familiar with C programming, we see some familiar functions here, puts, put string, printf, and scanf. So scanf, this is actually how we get user input. And we have a few variables here. I'm just going to label these. This is where the password is going to be stored. So I'll just call this user input password. And that's where we're at right now. So this is our window. It's asking for password. We have an exception. Oops. So I'm going to restart. Okay, so here's our window. We run through this. And puts, this is where it's going to be printing the first line. You can see right there. Printf, it's printing the second line to ask for the password. And then scanf, this is where we're going to input the password. So again, I'm just going to type password. Alright, now we're back here. So we're moving the password into a register here, which is going to be used in this function here. So let's go ahead and analyze this function. Okay, a lot of nitty-gritty details here, but if we just run through this, what happens is we see that this is the length of the input. So this is basically just string length. Whatever input we gave, it's calculating how big that is. And that function is going to return the length, which is 8. So then we compare that to 4, jump greater than or equal to. So if the input is greater than or equal to 4, then we're going to go over here. If not, we go over here where we have some instructions which will throw an exception. So basically this is not where we want to be. This tells us that whatever we input, it has to be greater than or equal to 4. So we just input password, that's 8. We're good to go. Can somebody email Calvin or text Calvin, say we're here? Thanks. Okay, so here we're clearing EBX, and then we're going to take our password and we're going to perform a hash on it. Alright, so ECX, this is our string length, which was 8, and we're doing a shift right. We're going to shift it right by 2. And if you break that down to binary, basically what that does is divide it by 4. So our input divided by 4, 8 divided by 4, that's going to give us 2. And you'll see why that's important in a second. So I'm just going to rename this function because we know this is the hash. And the hash happens in this loop here. So we're going to load 4 bytes from our string. Password is what we entered. And we'll see that those characters get loaded into the EAX register. Alright, 72, 73, 36. And I actually can't read the rest of that, but let me pull up an ASCII table here. '73, 73, 61, and one other number. Bye. So here we go. P, A, S, and S. So the reason that's backwards here, when we look at it in the register, 73, 73, those are the 2 S's, is because Intel reads numbers from memory in little endian format. Meaning if we have 4 bytes, PASS, they're going to be stored in memory backwards. So we have to keep that in mind when we use this for coming up with a memory address. Alright, so just to summarize what this hash does, it takes 4 bytes at a time of user input, adds it to the previous, rotates it to the left by 1 byte or 1 bit, and it does that for every 4 bytes. Alright? So we do that twice, and that's going to give us a number which we return.
Where did you get the 4 again?
4? For what?
For how many bytes it took?
Okay. So that's what this function does right here, load string, and it's loading the string as a D word. So because it's a D word, double word, one word is 2 bytes and double word is 4 bytes. And that's the size of a register. So it's loading the biggest size it can from memory into a register so that we can perform this hash function on it. Alright, so we get some value back from our hash. We stored in memory. Let's call this, I don't know, result. So we store the result here. Next thing we see, so we're moving this number, FBC3882C, we're moving this into EBX. And then we XOR our result and that constant right there. And you can see in the next instruction, whatever the result of that XOR is, we're going to be moving this number into that address. So what that tells us is that whatever numbers or characters we put into the input here as the password, that's going to have to point to a valid address once we hash it. So the reason that it throws an exception instead of telling us bad password, we'll see right here. That's because this is an invalid address. It's a bad password. It gives us a wrong address, and the computer doesn't have, or this program does not have that memory location mapped in. So because it's unmapped memory, it throws an exception saying, hey, I don't know where this address is. And the way this program was written is that, we'll see in a second here. Here, this is the exception handler. We probably missed that. But anyway, this wrong password statement, this is actually handled as an exception. So I guess one of the reasons that was done was so that it's not straightforward and it's a little bit harder to reverse engineer. Because I guess a more straightforward way to do that would be to have an if statement. If this is not correct, then say wrong password. But let's go through this again. We'll see that there's no direct place that we can tell where it says bad password. Let's see. Alright, anyway, so we know now that our goal is to get some kind of input where the result XORed with this constant value is going to give us a valid memory address. So what can we use as a valid memory address? If we just look through the code here, you can see that all of these are all zeros. And it goes on for pretty long over here. So if we go to the top, basically anything that starts with 401, that's an address that we can use. So let me pull up the PowerPoint again. Alright, so like I said, we know we can use an address that starts with 401 something something something, and we can use this right here, work backwards and get a valid address. Alright, so these highlighted bytes, like you saw, we need that to point to a valid address, and that result, that's going to come from whatever we input. So I did some of this on my own. You guys can do it at home as well, just for your own benefit. But one of the solutions that works is this string here. 6 apostrophe, open parentheses, ampersand, backtick, tilde, Q, and 1. So let's go ahead and punch that in. We'll see what that looks like in a minute. So go ahead and step through the code. And we'll punch in our password. Oops, wrong window. Alright, so the password was 6 apostrophe, open parentheses, ampersand, backtick, tilde, Q1. Alright, then we go through everything over here. Auto password, divide the length by 4. We're going to run our hash. Alright, now we have a result here. FB83 9998. Yeah, it's kind of hard to read. And then we load our key here. Set constant. Load the key. We XOR it. Alright, and now we can see that this is a valid address right here. So when we hit step over, we should not see an exception, because now this is a valid memory address. Alright, so this sequence of bytes got written to EAX. Let's see what it looks like. So let's see exactly here, what did it write. We go to this memory location right here, and in IDA Pro you hit the letter C. That'll show you code. And it tells us that it's clearing the EAX register and returning. So it looks like this is the actual end of the function, meaning this is how we want to exit. And if we look a little bit closer right here, what is this? So we're going to get a pointer to the exception handler. We're going to add 24, it looks like, to the stack. So you'll see that change over here. So here's our stack pointer. Alright, keep moving. So let's take a look right here. So good key. So we can see right here it was unobfuscating a string. So it was hiding the string so that we couldn't see it obviously. So we assume it's going to tell us that we entered a good password. Printf, pop, and then return. And then you can see we're returning here. This is the code that, let me go back. This is the code that was dropped here. And you see it tells us good password. So just to recap, we went through how this hash worked, and we just kind of worked backwards. We knew we had a valid range of addresses from 401.000 to 401.FFF. We worked backwards using the key and then the hash, and we found what valid user input we could use to get an address that would allow it to drop that code there. And if we run it again here, without the debugger or anything, 6. So you can see we basically cracked this program. We found a good password. Alright, so that's the Wiremask checksum challenge. Anybody have any questions about it? Go ahead.
So what you pretty much did to figure out code was take a valid address and shift it left then by 4 bytes? Or 2
Yeah,
bytes with it?
let's look at that again. Yeah, no, we went through it pretty quickly, but
It's the opposite of what the FMV did.
exactly. Yeah, so we know that we need an address right here, and we just work backwards from here. So this address we get by XORing with EBX. EBX came from this constant key right here. So whatever result we got from our hash, we have to be able to XOR with FBC3882C. We have to be able to XOR with that and get a valid address.
To go backwards from XOR, do you just XOR it again?
Yeah, exactly. So yeah, that's the starting point. When we're working backwards, this is where we would start with the key. And we're going to have to XOR it with our result, and we have to work backwards from there. So if we look at the hash, you take that first XOR, work backwards. So we see a rotate left right here. That means we're going to have to rotate right. We see add with EBX. That means we're going to have to subtract from EBX. And the only numbers that we're interested in are numbers that we can actually type with ASCII characters. So for example, that's really only anything between 21, which is exclamation, and 7E, which is the tilde. I did one actually where I used space, but it turns out space doesn't work because the way scanf works, scanf takes your input and it stops wherever there's white space. So that includes new line character and space. So if you put a space in, it's basically going to cut your input short.
So was it just like a guess and check kind of thing for choosing the address?
Yeah, we knew there was a range between 401.000 and pretty much 401.FFF. So anything there, that would work. I did a little bit of work on paper here. So I just wrote a few wildcards there and filled them in with whatever was going to make it easiest. Any other questions?
How did you know it was like a 401 success?
So that's because over here, the giveaway is that this is where the exception was being thrown. And we needed EAX to point to valid memory. So anything here really is valid memory. 402, I guess this would work. Maybe not, because the text section, your executable code, this is supposed to be read-only. I don't think you can write to this. But if we just look for sections of memory that are open, like I said, that's all of this. Sorry?
How did you get there?
So I just went from graph view over here and scrolled up. If you just scroll up, it's showing you all of the memory in a flat sense. So yeah, you can see that all of this memory here is being unused. This is all just a bunch of zeros, so yeah, that's how we know that we can use this memory over here.
What does the DB mean after the address?
DB, I can't remember what the D stands for, but B is for byte. It might be data, and it's a byte. Yeah, I can't remember exactly. But yeah, these are all just a bunch of zeros, so we can assume that it's unused. All right, any other questions?
So how long did it take you to work on this?
The first time, because I kept messing up, a couple hours. I kept messing up with my hex addition and subtraction, but yeah, the second time it was much easier. The first time my password was, I don't know, I think 32 characters, but after doing it again, like you saw, we can get it down to 8.
Is it more than one?
Yeah, basically any number you can use to get one of these addresses here, and there's a bunch of them.
So this is just one.
Yeah, and I think really there's an infinite amount of passwords because this hash happens in a loop. You can have a bunch of passwords that are 8 characters, 12 characters. It can be any length. So because it can be any length, yeah, I think it's infinite. But the minimum, I believe, is 8 because there's no ASCII characters. There's no ASCII character sequence of length 4 that'll get you a valid address, at least for this problem.
And how did you know that chunk of code was a hash? Was it
Which one?
the part that actually does the hash? Like, how did you know it was the hash? Like, was it like calling some standard library, some kind of MD5?
No, it's not a standard hash, and like you can see, it's not even a secure hash.
Yeah.
But yeah, we knew that the result of this function that's used to get this address right here, and just by the way that it mangles, the input, it's taking your input,
Yeah.
it adds to it, rotates it, adds to it, rotates it.
Yeah.
It's
Oh, so the users.
yeah, so it's hashing our input using this. All right.
So, this is a fairly simple program for like big complicated ones that you have to extract keys for. What more complicated things would you run into that you would be using?
Probably a lot more obfuscation. Yeah, off the top of my head, I can't name anything specific, but you would be seeing a lot more obfuscation. I mean, obviously, Microsoft is not going to use this to validate a license key or something like that. I don't know, things you could do. Maybe base it off of the memory, the data that's in the memory. Hard to say. Any other questions? No? Okay. Alright, thanks for watching then.